and, and give you a brief introduction to the history of computer vision.
Okay, let's start with today's agenda. So we have two topics to cover. One is a brief history of computer vision, and the other one is the overview of our course, CS231N. So we'll start with a very brief history of where vision come from, when did computer vision start, and where we are today. The history of vision can go back many, many years ago. In fact, about 543 million years ago. What was life like during that time? Well, the Earth was mostly water. There were few species of animals floating around in the ocean. And life was very chill. Animals didn't move around much. They don't have eyes or anything. When food swims by, they grab them. If the food didn't swim by, they just float around. But something really remarkable happened around 540 million years ago. From fossil studies, zoologists found out within a very short period of time, 10 million years, the number of animal species just exploded. It went from a few of them to hundreds of thousands. And that was strange. What caused this? There were many theories, but for many years, it was a mystery. Evolutionary biologists call this evolution's Big Bang. A few years ago, an Australian zoologist called Andrew Parker proposed one of the most convincing theories. From the studies of fossils, he discovered around 540 million years ago, the first animals developed eyes. And the onset of vision started this explosive speciation phase. Animals can suddenly see. Once you can see, life becomes much more proactive. Some predators went after prey, and prey have to escape from predators. So the evolution or onset of vision started an evolutionary arms race, and animals had to evolve quickly in order to survive as a species. So that was the beginning of vision in animals. After 540 million years, vision has developed into the biggest sensory system of almost all animals, especially intelligent animals. In humans, we have almost 50% of the neurons in our cortex involved in visual processing. It is the biggest sensory system that enables us to survive, work, move around, manipulate things, communicate, entertain, and many things. So vision is really important for animals and especially intelligent animals. So that was a quick story of biological vision. What about humans, the history of humans making mechanical vision or cameras? Well, one of the early cameras that we know today is from the 1600s, the Renaissance period of time, camera obscura. And this is a camera based on pinhole camera theories. It's very similar to the early eyes that animals developed, with a hole that collects lights, and then a plane in the back of the camera that collects the information and projects the imagery. So as cameras evolve, today we have cameras everywhere. This is one of the most popular sensors people use, from smartphones to other sensors. In the meantime, biologists started studying the mechanism of vision. One of the most influential work in both human vision or animal vision, as well as that inspired computer vision is the work done by Hubel and Wiesel in the 50s and 60s using electrophysiology. What they were asking the question is, what was the visual processing mechanism like in primates, in mammals? So they chose to study cat brain, which is more or less similar to human brain from a visual processing point of view. What they did is to stick some electrodes in the back of the cat brain, which is where the primary visual cortex area is, and then look at what stimuli makes the neurons in the primary visual cortex of cat brain respond excitedly. What they learned is that there are many types of cells in the primary visual cortex part of the cat brain. But one of the most important cells is the simple cells. They respond to oriented edges when they move in certain directions. Of course, there are also more complex cells, but by and large, what they discovered is visual processing starts with simple structure of the visual world, oriented edges. And as information moves along the visual processing pathway, the brain builds up the complexity of the visual information until it can recognize the complex visual world. So the history of computer vision also starts around early 60s. Block World is a set of work published by Larry Roberts, which is widely known as one of the first, probably the first PhD thesis of computer vision, where the visual world was simplified into simple geometric shapes. And the goal is to be able to recognize and reconstruct what these shapes are. In 1966, there was a now famous MIT summer project called the Summer Vision Project. The goal of this Summer Vision Project, as I read, is an attempt to use our summer workers effectively in the construction of a significant part of a visual system. So the goal is in one summer, we're going to work out the bulk of the visual system. That was an ambitious goal. 50 years have passed. The field of computer vision has blossomed from one summer project into a field of thousands of researchers worldwide, still working on some of the most fundamental problems of vision. We still have not yet solved vision, but it has grown into one of the most important and fastest growing areas of artificial intelligence. Another person that we should pay tribute to is David Marr. David Marr was a MIT vision scientist, and he has written an influential book in the late 70s about what he thinks vision is and how we should go about computer vision and developing algorithms that can enable computers to recognize the visual world. The thought process in his in David Marr's book is that in order to take an image and arrive at a final holistic full 3D representation of the visual world, we have to go through several processes. The first process is what he calls primal sketch. This is where mostly the edges, the bars, the ends, the vertical lines, the curves, the boundaries are represented. And this is very much inspired by what neuroscientists have seen. Hubel and Wiesel told us the early stage of visual processing has a lot to do with simple structures like edges. Then the next step after the edges and the curves is what David Marr calls 2.5D sketch. This is where we start to piece together the surfaces, the depth information, the layers or the discontinuities of the visual scene. And then eventually we put everything together and have a 3D model hierarchically organized in terms of surface, volumetric primitives, and so on. So that was a very idealized thought process of what vision is. And this way of thinking actually has dominated computer vision for several decades and is also a very intuitive way for students to enter the field of vision and think about how we can deconstruct the visual information. Another very important seminal group of work happened in the 70s, where people began to ask the question, how can we move beyond the simple block world and start recognizing or representing real-world objects? And think about the 70s. It's a time that there's very little data available. Computers are extremely slow. PCs are not even around. But computer scientists are starting to think about how we can recognize and represent objects. So in Palo Alto, both at Stanford as well as SRI, two groups of scientists have proposed similar ideas. One is called generalized cylinder, one is called pictorial structure. The basic idea is that every object is composed of simple geometric primitives. For example, a person can be pieced together by generalized cylindrical shapes, or a person can be pieced together by critical parts and their elastic distance between these parts. So either representation is a way to reduce the complex structure of the object into a collection of simpler shapes and their geometric configuration. These work have been influential for quite a few years. And then in the 80s, David Low, here's another example of thinking how to reconstruct or recognize the visual world from simple world structures. This work is by David Low, which he tries to recognize razors by constructing lines and edges and mostly straight lines and their combination. So there was a lot of effort in trying to think what is the tasks in computer vision in the 60s, 70s, and 80s. And frankly, it was very hard to solve the problem of object recognition. Everything I've shown you so far are very audacious, ambitious attempts, but they remain at the level of toy examples or just a few examples. Not a lot of progress have been made in terms of delivering something that can work in real world. So as people think about what are the problems to solve in vision, one important question came around is, if object recognition is too hard, maybe we should first do object segmentation. That is the task of taking an image and group the pixels into meaningful areas. We might not know the pixels that group together is called a person, but we can extract out all the pixels that belong to the person from its background. That is called image segmentation. So here's one very early seminal work by Jitendra Malik and his student Jianbo Shi from Berkeley, from using a graph theory algorithm for the problem of image segmentation. Here's another problem that made some headway ahead of many other problems in computer vision, which is face detection. Face is one of the most important objects to humans, probably the most important objects to humans. Around the time of 1999 to 2000, machine learning techniques, especially statistical machine learning techniques, start to gain momentum. These are the techniques such as support vector machines, boosting, graphical models, including the first wave of neural network. And one particular work that made a lot of contribution was using AdaBoost algorithm to do real-time face detection by Paul Viola and Michael Jones. And there's a lot to admire in this work. It was done in 2001 when computer chips are still very, very slow, but they're able to do face detection on images in near real time. And after the publication of this paper, in 5 years' time, 2006, Fujifilm rolled out the first digital camera that has a real-time face detector in the camera. So it was a very rapid transfer from basic science research to real-world application. So as a field, we continue to explore how we can do object recognition better. So one of the very influential way of thinking in the late 90s till the first 10 years of 2000 is feature-based object recognition. And here is a seminal work by David Lowe called SIFT feature. The idea is that to match an entire object, for example, here is a stop sign, to another stop sign is very difficult, because there might be all kinds of changes due to camera angles, occlusion, viewpoint, lighting, and just the intrinsic variation of the object itself. But he's inspired to observe that there are some parts of the object, some features that tend to remain diagnostic and invariant to changes. So the task of object recognition began with identifying these critical features on the object and then match the features to a similar object. That's an easier task than pattern matching the entire object. So here is a figure from his paper where it shows that a handful, several dozen SIFT features from one stop sign are identified and matched to the SIFT features of another stop sign. Using the same building block, which is features, diagnostic features in images, we have, as a field, has made another step forward and start to recognizing holistic scenes. Here's an example algorithm called spatial pyramid matching. The idea is that there are features in the images that can give us clues about which type of scene it is, whether it's a landscape or a kitchen or a highway, and so on. And this particular work takes these features from different parts of the image and in different resolutions and put them together in a feature descriptor. And then we do support vector machine algorithm on top of that. Similarly, a very similar work has gained momentum in human recognition. So putting together these features, we have a number of work that looks at how we can compose human bodies in more realistic images and recognize them. So one work is called the histogram of gradients. Another work is called deformable body part models. So as you can see, as we move from the 60s, 70s, 80s towards the first decade of the 21st century, one thing is changing, and that's the quality of the pictures. We're no longer, with the internet, the growth of the internet, the digital cameras, we're having better and better data to study computer vision. So one of the outcomes in the early 2000s is that the field of computer vision has defined a very important building block problem to solve. It's not the only problem to solve, but in terms of recognition, this is a very important problem to solve, which is object recognition. Well, I talked about object recognition all along, but in the early 2000s, we began to have benchmark data set that can enable us to measure the progress of object recognition. One of the most influential benchmark data set is called Pascal Visual Object Challenge. And it's a data set composed of 20 object classes. 3 of them are shown here: train, airplane, person. I think it also has cows, bottles, cats, and so on. And the data set is composed of several thousand to 10,000 images per category. And then the field, different groups develop algorithm to test against the testing set and see how we have made progress. So here is a figure that shows from year 2007 to year 2012, the performance on detecting objects, the 20 objects in the image, in the benchmark data set has steadily increased. So that was a lot of progress made. Around that time, a group of us from Princeton to Stanford also began to ask a harder question to ourselves as well as our field, which is, are we ready to recognize every object or most of the object in the world? It's also motivated by an observation that is rooted in machine learning, which is that most of the machine learning algorithms, it doesn't matter if it's graphical model or support vector machine or AdaBoost, is very likely to overfit in the training process. And part of the problem is visual data is very complex. Because it's complex, our models tend to have a high dimension of input and have to have a lot of parameters to fit. And when we don't have enough training data, overfitting happens very fast, and then we cannot generalize very well. So motivated by this dual reason, one is just want to recognize the world of all the objects. The other one is to combat the machine learning, overcome the machine learning bottleneck of overfitting. We began this project called ImageNet. We wanted to put together the largest possible data set of all the pictures we can find in the world of objects and use that for training as well as for benchmarking. So it was a project that took us about 3 years, lots of hard work. It basically began with downloading billions of images from the internet, organized by the dictionary we called WordNet, which is tens of thousands of object classes. And then we have to use some clever crowd engineering trick and method using Amazon Mechanical Turk platform to sort, clean, label each of the images. The end result is an ImageNet of almost 15 million or 40 million plus images organized in 22,000 categories of objects and things. And this is the gigantic, probably the biggest data set produced in the field of AI at that time. And it began to push forward the algorithm development of object recognition into another phase. Especially important is how to benchmark the progress. So starting 2009, the ImageNet team rolled out an international challenge called ImageNet Large Scale Visual Recognition Challenge. And for this challenge, we put together a more stringent test set of 1.4 million objects across 1,000 object classes. And this is to test the image classification recognition results for the computer vision algorithms. So here's the example picture, and if an algorithm can output 5 labels, and the top 5 labels includes the correct object in this picture, then we call this a success. So here is a result summary of the ImageNet challenge, of the image classification result in from 2010 to 2015. So on the x-axis, you see the years. On the y-axis, you see the error rate. So the good news is the error rate is steadily decreasing to the point by 2012, the error rate is so low, it's on par with what humans can do. And here, by human, I mean a single Stanford PhD student who spent weeks doing this task as if he were a computer participating in the ImageNet challenge. So that's a lot of progress made. Even though we have not solved all the problems of object recognition, which you'll learn about in this class, but to go from an error rate that's unacceptable for real-world application all the way to being on par with humans in ImageNet challenge, the field took only a few years. And one particular moment you should notice on this graph is the year 2012. In the first 2 years, our error rate hovered around 25%. But in 2012, the error rate was dropped almost 10% to 16%, even though now it's better, but that drop was very significant. And the winning algorithm of that year is a convolutional neural network model that beat all other algorithms around that time to win the ImageNet challenge. And this is the focus of our whole course this quarter, is to look at, to have a deep dive into what convolutional neural network models are. And another name for this is deep learning by popular, a popular name now is called deep learning. And to look at what these models are, what are the principles, what are the good practices, what are the recent progress of this model. But here is where the history was made, is that around 2012, convolutional neural network model or deep learning models showed the tremendous capacity and ability in making good progress in the field of computer vision, along with several other sister fields like natural language processing and speech recognition. So without further ado, I'm going to hand the rest of the lecture to Justin to talk about the overview of CS231.